So exactly a week ago, we started talking about molecular shape and how this is going to be related to then properties of molecules, physical properties, like are they polar, are they nonpolar? And then that's going to tell us a lot about how these molecules then interact with each other, right? So this is going to segue into what we call intermolecular forces, right? So we start with atoms. What are atoms comprised of? What are the forces that hold atoms together? How do the electrons fill up the energy levels in the atoms? That's what you just had your exam on. Then we talked about how the atoms then interact with other atoms to form bonds, ionic versus covalent bonds. And then in the next week or so, or today, what we're going to finish up with is now we've built up the idea of these bonds and how they have specific properties that or give properties to the molecule that they are a part of. And now those molecules are going to interact with other molecules, right? So we're kind of building up this scale of what it is that we're looking at. So last time we talked about molecular shape. And molecular shape depended on what? What determines the molecular shape, the shape of a molecule? It determines the polarity. It's usually the other way around. Molecular shape will determine the polarity. So what determines the molecular shape, though? The central atom. So there's going to be something related to the central atom, right? So this is going to be relatively simple molecules that we look at the shape of. So this is going to be related to the central atom, right? And then specifically what thing on the central atom, or what things on the central atom? Electrons, right? So electrons are going to be involved, right? So there's going to be electron groups on the central atom, right? So electron groups on the central atom. Right, so the central atom determines the shape and the electron groups on the central atom. And what were the two different electron groups that we had? Bonding and non-bonding pairs, right? So bonding pairs and non-bonding pairs. Right, those are our two electron groups. And so bonding pairs are what? Or what's a simple way we could describe bonding pairs? Bonds between the atoms, right? So the bonds between the atoms, right? So that's electron group because there's electron density, or there's electrons in that bond, right? So that counts as an electron group. In a simple way, so this is the electrons in bonds to central atom. And the simple way that we could determine this, does anyone remember what the simple way that we determined this was? If we look at a molecule, how can you determine the number of bonding pairs right away? It will be related to the valence, but not necessarily directly valence electrons or anything. The group number gives you the number of valence electrons. That tells you how the bonding happens.
Is it like when there's the dot?
Those are Lewis dots, right? So Lewis dots represent electrons that are not involved in bonding, right? So that's actually going to be related to our non-bonding pairs, and specifically lone pairs when we look at that, because that's how they'll exist unless we have a charged atom. But if I gave you, let's say, a molecule like PF3, for example, how do you determine the number of bonding pairs? Yeah, the number of atoms that are bonded to the central atom, right? That's the easiest way to determine, right? So the easiest way to determine the number of bonding pairs is number of atoms bonded to the central atom, right? And the reason that we make that distinction is the number of atoms bonded to the central atom is because we can form multiple bonds between atoms, right? We can form double, single, and triple bonds. But those don't affect the number of bonding pairs. So it's not the number of bonds that are important. It's the number of atoms bonded to the atom, the central atom.
So if there was another atom outside of the PMF, is that
Yeah, so if there's something like that, you're saying? Yeah, so that would then mean we have 4 bonding pairs instead of 3 when I add the H there, right? And in this case, right, if we look at this molecule, F, 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 it's going to look something like this if you were to draw the Lewis structure, right? The number of bonding pairs here is the number of fluorine atoms that are bonded, right? And again, molecular shape is just a made-up way that we rationalize the way the shapes that molecules make. So it's, okay, I'm just curious what it is.
So what about when there's like 5?
Then how many bonding pairs did you have?
Like how would that look? I'm saying.
So those come to more complicated shapes, so it depends on the number of bonding pairs and lone pairs what the shape that you would get. If you have something like 5, like PF5, for example, if this is, we're not going to be going over shapes like this in our class. We'd have P, something like this, right? And the name of this shape is trigonal bipyramidal, right? So this is trigonal bipyramidal because if we look at the shape that these form, altogether, it's 2 pyramids that are kind of attached to each other, right? So this is trigonal bipyramid. So again, these are just rationalizations of the shapes that molecules make. And the rationalization is that, well, all of these bonds and lone pairs all have electron densities. Electrons have what charge? Negative, so they like to do what if they come in contact with each other? They like to repel each other, right? So if you have a bunch of electron groups on an atom, they're not going to be all next to each other on one spot, right? They're going to try and disperse around the atom to then minimize, that repulsion that they feel to each other, right? So this is just the rationale for how these shapes are made. The very specific shapes, remember last time we were asking about there's different bond angles if you have a water molecule versus a sulfur dihydride, for example, like those specific angles are going to be different, but the idea behind the repulsion is still the same. So that's why Vesper, right? So this is all under the acronym Vesper, which was valence electron, shell pair repulsion, right? So it's basically saying the repulsion of electrons is what guides the shape of molecules. And whether it's a lone pair or it's a bonding pair, those all have electron density. So those all should affect the shape of the molecule. And why is it that we only care about the bonding pairs and lone pairs? Well, the core electrons aren't involved in bonding at all, right? Those kind of just form like a spherical hard shell on the inside, and it's the outermost electrons that are moving around the most, right? So the number of atoms, that gives us the number of bonding pairs, right? And what about the number of non-bonding pairs? How do we determine that? Who remembers? This would be the lone pair electrons, right? These are lone pair. The number of lone pair, I'll write this a little neater. The number of lone pair electrons. So when I looked at that PF3 up there, how many non-bonding pairs do we have? 2, or we have 1, right? Because it's a pair of electrons, this means 2 electrons, right? So when you're drawing your Lewis structures, as we get more comfortable, it's important that if we see 2 electrons, that we don't put them at different spots on the atom, we'll start drawing them together because that's how they actually exist on the atom. They exist as a pair. We call that a lone pair of electrons. And so normally if we have 3 bonding pairs and 0 lone pairs, we have what's called a trigonal planar shape, which means it's just like a flat triangle, right? As soon as we add this lone pair to the central atom here, that lone pair now pushes all of those atoms down and it distorts the shape, right? So that's why we get a new shape when the lone pair exists there. Again, lone pair is just another form of electron density or a negative charge, and they want to spread out around the atom as easy as they can. All right, and then these then determined the shape, right? So the important thing when we're determining molecular shape is the number of atoms bonded to the central atom and the number of lone pair electrons, right? So the number of lone pairs. All right, so what were the different shapes we had? So we'll have bonding pairs, lone pairs, and the shape.
Pyramidal.
We had pyramidal, or we called it trigonal pyramidal. I'm not going to put these in any order, just the order that you guys gave them to me, right? So trigonal pyramidal, how many bonding pairs and how many lone pairs did that have? Yep, we had 3 bonding, right? Pyramidal, we think, okay, this is going to look like a pyramid somehow. We don't really look at the lone pairs when we're looking at the shape, but we're looking at the bonding pairs. That's what determines the shape. Like, we don't imagine seeing the lone pair electrons, but we know they affect the shape. We're looking at the overall shape with the bonding pairs. So 3 bonding pairs and 1 lone pair. And so that was like the molecule that we just had. This would be something that is trigonal pyramidal, right? And we'll talk about the properties in a second. What other shapes did we have? We had a linear molecule. And how many bonding pairs and how many lone pairs does that have?
No lone pairs, right?
Yep, we have 0 lone pairs
And 2 bonding?
and 2 bonding pairs, right? And so an example we had of that was carbon dioxide, right? And this is where it's important that we recognize that there isn't, even though the bonding pairs has to deal with bonds and electron density, it's not the number of bonds that are there, right? Because there's 4 bonds attached to the central atom here, right? There's 4 bonds, but there's only 2 atoms that are bonded to it. So that's why it's linear and not tetrahedral, for example. All right, what was another shape that we had? We had a bent molecule. And it's nice that we did that right after linear, because bent, there was 2 different ways we could have bent molecules. What was one? How many bonding pairs? 2 bonding pairs. And how many lone pairs? 2, that was 1. And then there was also, I'm going to put this in green, 2 and then 1, right? So there's 2 ways that we could have bent molecules. And one that we looked at, for example, was sulfur dioxide, which was SO minus, lone pair, double bonded to O. We had sulfur dioxide, there's a little positive charge. And so what we see is that this molecule now has a lone pair on the central atom, right? We don't care about the lone pairs that are on the outside atoms, we only care about the lone pairs on the central atom. And so we have originally something that looks linear, but now because there's a lone pair there, lone pair affects how the bonds arrange themselves around the central atom, so it distorts the molecule. How does it distort it? Well, these bonds want to get away from that lone pair, right? So that moves to a bent shape after. So really, this looks something like that, right? Because they're trying to move away from the lone pair, so both of the bonds get bent down.
Is it because the,
And this should be a green. Go ahead, Summer.
the molecular weight is uncommon? Is that why it's bending?
It's not bending because the molecular weight is going up. It's bending because this lone pair is electron density, right? And electrons are what charge?
Negative.
Negative, right? And electrons are also existing in these bonds, right? These bonds between these covalent bonds, right? And those electrons have what charge on them? Negative as well, right? So they want to move away from that lone pair. So the existence of the electrons, even though they're not involved in bonding, right? These are not involved in bonding. They push the other electrons away. So that distorts the original linear structure. Whereas in carbon dioxide, we didn't have any lone pairs on the central atom, right? So the easiest way that those will get away from each other is just on exact opposite sides of the molecule, right? So it's 180 degrees away from each other, right? They'll just get as far away as they can. Adding the lone pair there then just distorts the structure. And then we had another one, it was H2O, right? This is another bent molecule. And now this, I'm not going to draw the bulbs, you can. This central atom has 2 lone pairs on it, right? There's still electrons in these bonds between oxygen and hydrogen, So those are gonna move away from both of these lone pairs, right? So it's still gonna be a bent structure like this, except now we have double the electron density on top, so it's gonna push those hydrogens down farther. If you go farther on in chemistry, you'll learn both of these have different angles right here, right? Which one do you think is gonna be a larger angle, this one or that one? If this is the angle I'm talking about. It should be the one on the left right here, right? Because this one only has one lone pair pushing down, right? So it's not gonna push them that far down. But this one has two lone pairs pushing down, so they're gonna go a lot farther down, which means they're gonna be closer together. So this, if you guys go on in chemistry, this will be about 120 degrees, and this will be about 107 degrees. All right, we're not worried about that. I'm not gonna be testing you guys on that. But in the future, if you continue with chemistry, you will learn about the different bond angles, and that has to do with the specific type of bent structure that you have. So there's two ways that we have bent molecules. And how do we think of a bent molecule? Where it's a linear molecule now that has lone pairs that are distorting the structure. All right, what other shape do we have? We had a tetrahedral molecule. Make sure I didn't give myself enough room. We had tetrahedral. And so tetrahedral has how many bonding pairs? 4 bonding pairs. And how many lone pairs? 0 lone pairs. And so an example of something tetrahedral would be methane, which is carbon bonded to four hydrogens. This is a tetrahedron, right? It has 4 triangular faces right there. That's just what that shape is called. And what was the last shape that we had? Trigonal planar, yep. Trigonal planar. Right? And this is like trigonal pyramidal, except what? What's the difference between the bonding pairs and the lone pairs for trigonal planar? There's no lone pairs, right? So 0 and 3. An example of this was when we looked at formaldehyde, like that, right? We see that even though we have 2 bonds here between carbon and oxygen, that still only counts as 1 bonding pair, right? Because the bonding pairs is the number of atoms that are bonded, not the number of bonds attached there, right? So that's that's an easy spot to kind of get mixed up there. The number of atoms that are bonded to our central atom. And there's no lone pairs, right? So if you turn this on its side, it's like a plane, right? Plane is like a piece of paper. When you turn it to the side, it's going to be flat. Whereas trigonal pyramidal has a lone pair there that distorts it. So when you turn it to the side, it looks bent. And it bends the triangle into a shape of a pyramid, like that. And so these are all the shapes, looking at bonding pairs and lone pairs. And we talked about how does this affect the properties of the molecule. So is it polar or is it nonpolar? And so let's go through, and we'll have a little blue symbol here. It'll be the polarity of each of these shapes. And so for trigonal pyramidal, what's the polarity of that? It should be always polar, right? Trigonal pyramidal is always going to be polar. So this is always going to be polar. How do we justify that? Well, this lone pair, right? What's more electronegative, phosphorus or fluorine? Fluorine, right? Fluorine is the most electronegative element, right? So it's more electronegative. So it's going to be pulling or pushing electrons. It'll be pulling them, right? So each of those fluorines is going, and they all have the exact same electronegativity, right? So they're going to be pulling equally. Each of those is going to be pulling electrons, creating little dipoles in these polar bonds here, right? And they're all going to be pulling down a little bit. They're all pulling in opposite directions in the triangle, right? Equal and opposite directions in the triangle. But since they're all pulling down slightly, there's no upward force that's pulling electrons up at all, right? So that creates a net dipole, on the molecule. Why? Because there's nothing to cancel out all the little dipoles that are pointing down, right? Those are all pointing down. We don't have an atom like we do in our tetrahedral structure that is pulling directly straight up, right? Those cancel out with everything that's pulling down in each of these cases. But for trigonal planar, we don't have that. So trigonal planar molecules, or sorry, trigonal pyramidal molecules are always going to be polar. What about, Summer?
But for the tetrahedral, is that also gonna be polar?
Tetrahedral, so let's skip ahead to tetrahedral. So tetrahedral, is that going to be polar or nonpolar usually?
Non-polar.
We put nonpolar, right? And then I put a little asterisk. That's not asterisk, that's a star. I put a little asterisk there, right? And why do I put a little asterisk there for nonpolar? So we say it's going to be nonpolar most of the time, right? Why is it only nonpolar most of the time? How would we change this structure to be polar?
Changing the atom.
Yeah, if we change one of these hydrogens for an atom with a different electronegativity, now all of a sudden they're not pulling in equal and opposite directions because one side is pulling different than the other. So that'll create a small, net dipole on the molecule, right? So it can be polar with different atoms. Right, so for example, if instead of there, I had a fluorine there, all of a sudden now this fluorine is pulling a lot more than these hydrogens are. And so that's going to mess with the polarity of the entire molecule. What about linear? How would we classify that? It'll be nonpolar as well. And then we'll also put the asterisk there because we can do the same thing with a linear molecule, right? If we have something that's like carbon dioxide, if we replace one of the oxygens with sulfur, now that side pulls differently than the side with oxygen. So there can be a net dipole. What about a bent molecule? Those are always going to be polar, right? So bent molecules, similar to trigonal pyramidal, the lone pairs distort the structure. Things aren't pulling equally and opposite anymore, and you're going to have a net dipole moment on the molecule. For example, water is a very, very polar molecule. And what about trigonal planar? Nonpolar, and then we'll put the asterisk there as well, because if we replace an atom, that's something that has a different electronegativity. So in this case, would you classify this molecule as polar or nonpolar, you think? This one should be polar, right? Because this oxygen pulls a lot more than the hydrogens, right? So that means the dipole is going to be going up here, and you're going to have little dipoles pulling in this direction. They pull equally in left and right, but they don't pull enough to cancel out how much oxygen is pulling, right? So that's why that's going to be a polar molecule. Right, so we have to think about the shape and then also the specific bonds there too, right? How polar a bond is depends on the electronegativity, and then the number of bonding pairs and lone pairs determine the shape. Those in combination give us whether the molecule is polar or nonpolar. Right, so there's a lot to keep track of, right? And so, for example, if you're given, well, what is the polarity, and we'll do this in a second, of these molecules determine the molecular shape, and if they're polar or nonpolar, you're given the chemical formula, you have to draw the Lewis structure, then you have to determine the shape, then you have to analyze the bonds, are they polar or nonpolar, and then look at how does that affect whether the molecule is polar or not polar, right? So it's a lot of things that go into just determining if a molecule is polar, right? There's like 4 different steps in that. Okay. So let's look at an example. Polar is unequal sharing, right? Because so the way we can remember that is a dipole is what makes it polar. So if there is a dipole, there's a difference in electronegativity, so that makes it polar. If there's no dipole, that is nonpolar. Right, so no dipole, nonpolar, dipole, polar. All right. So determine if let's see, what molecule do I want to look at? CH3Cl is polar. All right, so see if you can figure out if chloromethane is polar. Lewis structure, what's the essential atom?
Carbon.
Carbon, right? It's going to be the least electronegative because halogens and hydrogens like to go outside, right? So carbon has 4 valence electrons. Chlorine has how many? 7 because it's in what group? 7. And then hydrogen has how many? 1, right? So when we connect the dots, our Lewis structure is going to look like this. And if we went through and checked our octet rule for this molecule, we would see that all the atoms satisfy their octets except what 3 atoms? What 3 atoms don't need to satisfy an octet? Hydrogen, right? Because it needs 2, right? It needs a doublet. Right, so this is our valid Lewis structure here. So now that we have the Lewis structure, we can determine the number of bonding pairs and lone pairs for which atom? The carbon, right? Because that's the central atom, right? We're looking at the central atom when we look at the shape, right? So first step is to draw Lewis structure. Second step is going to be determine the shape, right? And so how many bonding pairs and how many lone pairs do we have? 4 bonding pairs. And how many lone pairs on carbon? 0, right? We have 0 lone pairs on carbon here. Why? Because there's no non-bonding electrons. Even though it satisfies the octet, we gain all those electrons from covalent bonds, not from lone pairs that exist on carbon. So there's 0 bonding pairs. So what shape is this? Tetrahedral, right? So this is tetrahedral. So now that we have the shape, then we'll analyze the shape in combination with the different bonds that are on this molecule to determine if it's polar or not. So we're going to use shape plus polarity of bonds to determine if the molecule is polar. So do we see any bonds in this molecule that are more or less polar than the other ones?
Yeah,
Which one?
the chlorine.
The chlorine, right? Because the chlorine pulls stronger, it's a more electronegative element than hydrogen, right? So this bond here is going to be a more polar bond, right? So this is a more polar bond than these 3 bonds right there, which means that this is going to pull, even though they're all pulling in exact opposite directions, this one's pulling more unequally in that direction. So we don't get any cancellation of the dipolar. So usually tetrahedral is polar or nonpolar? Nonpolar, right? But in this case, because you have a chlorine there, that makes this a polar molecule. Right, so that makes this polar molecule because of CCl bond. And so that's our answer. Right there. Summer?
Should that chlorine have 3 lone pairs on it?
That one should have 3 lone pairs on it. So as you go farther in chemistry, people will usually leave lone pairs off of atoms, especially atoms that they're just implied that the lone pairs are there, right, to satisfy the octet. Otherwise, it would have a charge or something on it. But yeah, for right now, we should draw our lone pairs. It's good for pointing that out.
So on its
if it was just a tetrahedral molecule with either 4 hydrogens or 4 chlorines in those cases, you have the exact same dipole in each direction. Because, yeah, because there's one that's different. Yeah, now they're still pulling in exactly opposite directions, but they're pulling unequally, right? So there's going to be a net direction that's pulling more than the other directions. And so, like I said, you're not going to have to ever draw the dipole arrows and stuff, but that give you an idea of why adding a chlorine makes the molecule polar, whereas before it was a nonpolar molecule, if all of the atoms were the same. All right, let's do another example, and then we'll start talking about intermolecular forces. All right, any other questions on this before I go to the next one? All right. Is NFCl2 a polar or nonpolar molecule? So what's the first step? Draw the Lewis structure. And then we determine the shape. So I'll give you 3 minutes to do that. So what's the Lewis structure look like? What goes in the center? Nitrogen, right? So if you thought, that would be a good question to ask. If you thought that L was an I, then I could understand where that confusion would come through. But that's supposed to be Cl2. So that's for chlorine, right? So I understand that confusion. That's a good point. I'll try and draw that a little neater next time. So we're going to assume that nitrogen, right? Nitrogen is more or less electronegative than chlorine and fluorine. It's less electronegative, right? Because it's left on the periodic table. It's a little hard to compare chlorine and fluorine, but chlorine is the 4th most electronegative element, right? So we have nitrogen in the center, and we also know halogens like to go where? Outside, right? So that's going to be outside. So we have N, then we're going to have F, Cl, and Cl. So is this my finished Lewis structure for this? One second, let me finish drawing. All right, this is my finished Lewis structure for this compound. Am I missing anything here?
Yeah, the lone pair.
The lone pair on nitrogen, right? Because if I don't have the lone pair, then I don't satisfy the octet rule. In this case, you could put the chlorines and fluorines when you're drawing your Lewis structure in any position around the nitrogen. I draw it like this because I figure that I have an idea what the shape is gonna be before I draw it, which you get just with more experience. But, huh?
You also need 2 on the fluorine, right?
No, there's only one fluorine atom, right? So what determines the number of atoms in a covalent molecule? Given the chemical, or in any molecule. Why don't I need 2 fluorines here?
No, 2 dots, 2 more dots.
Oh, 2 more dots. Oh, I think they got deleted on accident, yeah. Yeah, 2 more lone pairs. Okay, I thought you were saying I need a whole other fluorine atom. I was like, no. All right, so that's my Lewis structure. This is a valid Lewis structure. We check the octet rule for everything. It would be satisfied. And so what's the shape of this molecule? This is going to be trigonal pyramidal, right? So this will be trigonal pyramidal. And how do you know that?
Because there's 3 bonding pairs.
There's 3 bonding pairs and what?
1 lone pair.
And 1 lone pair. On what?
The central one.
The central atom, which is nitrogen, right? On nitrogen, right? Nitrogen is the one that determines the shape. That's why we need to make sure our Lewis structure is correct, right? Because if we put one of the other atoms in the center here, now all of a sudden we don't have a valid Lewis structure. We can't tell what we're doing, right? So we're using what we did previously now to build upon that. All right, so is this going to be polar or non-polar, you guys think, right? The third step is to analyze the shape. Shape plus bonds. And so, yeah, we know this is going to be polar. And so why is this going to be polar?
Because the bond between the nitrogen and fluorine.
We have one asymmetric bond here, right? One where that fluorine is pulling more than the chlorines. And then what else? What's the main reason this is going to be polar? Because it's trigonal pyramidal, right? And trigonal pyramidal is always going to be a polar molecule. Why? Because that lone pair is always distorting the shape. So we're pulling in not equal directions, right? We don't have all of them pulling exactly opposite to each other. There's going to be a net pull going down or up in this case. This is always going to be polar because trigonal pyramidal is always polar. All right, any questions on that? No? Okay. So shape then tells us if a molecule is going to be polar or not. And that leads us into our next topic, which are going to be what are called intermolecular forces. Right? So intermolecular forces are forces of attraction or repulsion between molecules of a molecular substance. So all types of molecules, covalent or ionic, have these forces. And so these forces then determine a lot of the properties of the material, right? Things like boiling point, vapor pressure, all of these things depend on how tightly these molecules are bonded to each other. Right? And so this means how do these molecules arrange themselves in solution or in solids. So the types of intermolecular forces determine that. And if you don't have chemical reactions, this is the driving force for a lot of things. So a lot of biological processes, for example, you're not necessarily changing one molecule from one to another, but you have interactions between lipids and water that then gives you the cellular membrane, right? So these intermolecular forces determine how the membrane in your cells shape themselves and allow for things to pass through or not pass through. All right, so intermolecular forces govern a lot of the world around us. And so in covalent molecules, there's 3 types of intermolecular forces that we're going to learn about. And just because I didn't put it on the previous page, usually I just abbreviate intermolecular forces as IMFs. So there's going to be van der Waals, or London dispersion forces. All right, so you'll hear both of those used interchangeably, van der Waals forces or London dispersion force. Van der Waals, because he had an idea of what those were before we knew what atoms were, and London dispersion for the physicists that actually proved its existence. Then we're going to have dipole forces, which now that we've determined if how molecules can be polar or nonpolar, these are how polar molecules are going to feel attractions to each other when they're in solution or in a solid together. Right? So these dipoles, the reason they're important is because if you have a permanent dipole on a molecule, that's going to determine how you orient yourself with another molecule that has a permanent dipole or a molecule that doesn't have a permanent dipole. And the last one that we're going to determine or look at are going to be hydrogen bonding. And hydrogen bonding is just going to be a very specific type of dipole interaction. It's basically going to be where you have very electronegative elements bonded to hydrogen, creates a very strong dipole that then introduces a special type of dipole-dipole force. And so all of these forces are determined by electrostatics. Right, so all of these things, like in chemistry, is just determined by how charges attract and repel each other, right? Once you get into stronger forces, like the strong force, weak force, those, a little bit deeper in physics. For chemistry, we're worried about electrostatics. And I'll put in a star here that we also have ionic compounds. Ionic compounds, if we have a full charge separation, for example, something like sodium and chlorine, in this molecule, chlorine has what charge? Yep, -1, right? We have a minus charge on the chlorine, and what charge on sodium? Positive, right? Because we don't share electrons, we don't pull electrons in ionic compounds, we completely transfer them, right? So they have a full charge separation. So in these ionic compounds, the dipoles, there's still a dipole between these two atoms, but it's the largest dipole that we can have, right? Because we have a full charge separation in ionic compounds. So ionic compounds are going to have stronger intermolecular forces than any covalent compounds. These are dipole forces, stronger than any covalent IMFs. Right, so that's important to think about. And if you think about, it's a little counterintuitive, right? Because ionic bonds between two atoms are not as strong as covalent bonds between two atoms. It takes more energy to separate a covalent bond than it does two ions from each other. However, when you look at an ionic compound like sodium chloride, this is a molecule that interacts with another molecule of sodium chloride. Those are going to have stronger attractions for each other, the molecules, than two covalent molecules. How do you remember this? Well, if you think about trying to evaporate something like a crystal of salt, right? You can put salt on a hot pan and it'll just stay solid salt for a very, very high temperature. Whereas if you add water, which is a covalent molecule, and water has all of the intermolecular forces, so it's going to have very, very strong intermolecular forces, water will still evaporate before the salt starts to melt. And if you're talking about then vaporizing the salt, right, you're probably going to have to get to extremely high temperatures before you start putting salt into the gas phase. Right, so ionic compounds are always going to have stronger intermolecular forces, the forces that hold the molecules together, than covalent compounds. Covalent bonds are stronger, but the forces between covalent molecules and other covalent molecules are weaker. Right, so that's an important distinction to have here. The intermolecular forces for ionic compounds are larger than covalent compounds, but the bonds in the molecule are weaker than each other. Right, because we're not actually, when we evaporate water, we're not going through a chemical change. We're not turning water into oxygen gas and hydrogen gas. We're just putting the water molecules into the gas phase. If we were talking about breaking the bonds in water, that would take more energy than breaking the bonds in salt. All right, any questions on that?
Wait, so you're saying that for the ionic compounds, it's stronger, the force?
The force between molecules is stronger, right? So if we have sodium chloride and another sodium chloride atom, they have really big dipoles because they have a full charge separation. So those two molecules interacting is strong. Whereas water, we have water and another water molecule, those interact through van der Waals, dipole-dipole, and hydrogen bonding, right? That force is weaker than the force between two sodium molecules interacting with each other. However, if I go to a water molecule and I try and rip apart the hydrogen and the oxygen, that's going to take more energy than pulling apart sodium and chlorine within the molecule, right? So there's these scales that we've built up, right? The atoms, we fill in the electrons in the atoms. That determines how the atoms bond with other atoms. That's a bond between two atoms, ionic or covalent. Covalent bonds are stronger than ionic bonds. Now we go up one level. How do the molecules then interact with other molecules? So sodium chloride, salt interact with another salt molecule. That's a stronger bond than water molecule interacting with another water molecule, right? So it's kind of like it goes up and then down, right? We go to covalent molecules, those bonds are stronger, but then we go to molecular interactions, intermolecular forces between molecules, then it gets weaker for covalent molecules. Yeah, so basically, the short form is if you see an ionic compound and it asks you to rank the strength of the intermolecular forces, ionic compounds will always have the strongest intermolecular forces compared to covalent compounds. So what does that mean? You need to be able to identify if a compound is ionic or covalent, right? And so how do you know if it's ionic? Metal and a non-metal, right? See metal and a non-metal, instantly you know, okay, these are going to be strongest intermolecular forces in here. Two nonmetals, covalent molecule, that's going to be weaker. How do I rank different covalent molecules? Well, now I need to actually look at the structure of these covalent molecules, right? So first, get rid of the ionic compounds, that's the strongest. Then we analyze the covalent molecules. Okay, so let's talk a little bit about what these intermolecular forces actually are for covalent molecules. So van der Waals forces, or London dispersion forces, these are going to be forces between nonpolar molecules. And so what happens, or atoms, it can be nonpolar molecules or atoms. Here we have two neon atoms, right? Neon is inert, it doesn't like to react. And they have electrons that are kind of floating around them, right? What happens is, as we move through time, those electrons kind of slosh around, they go back and forth. And so there might be an instant where electrons are more on one side of the atom or molecule than they are on the other, right? So they moved over, and they'll slosh back and forth. However, after a little bit of time, if that neon atom is next to another neon atom, now because I've sloshed these electrons over to this side, and it's next to another atom, what are these electrons going to do to the electrons in the neon atom next to it? Electrons are what charge? Negative, right? So when they get close to the electrons of the other neon atom, what are they going to do? They're going to push them away a little bit, right? And now, this pushing of electrons in the neighboring atom induces the electrons in this atom being pushed aside. And so now we have two temporary dipoles, right? So this is what we have, temporary dipoles, because they're going to go back and forth, but the fact that this pushed over just by chance, random chance, because we're not at zero temperature in the universe, that means that it pushes these electrons over here. And then what's going to happen is they're going to slosh back the other way, and you kind of get this synchronization effect of two atoms or molecules that are next to each other. So even though they're nonpolar, because they have no permanent dipole, they can induce a temporary dipole in molecules next to them. And so this temporary dipole then induces dipole in the molecule or atom next to it, and then they synchronize with each other. And that synchronization creates a little force of attraction between them. And so when I synchronize, it just means kind of they go in rhythm, right? So they kind of like, at first everything's chaotic, temperature's bumping around and stuff, and then they kind of find a rhythm once they're right next to each other. And when they do that, that means that there's going to be a force of attraction between those. Because when these ones slosh to the right, they're going to induce a temporary dipole. This partially negative side is attracted to this partially positive side. And then when they go back the other direction, this partially positive side is attracted now to this partially positive side. So they go back and forth, they synchronize, and then they introduce a small force of attraction, right? So that's what I'll put here. These are small, relatively small forces of attraction. And so what causes it is it causes a temporary dipole, induces another dipole on a neighboring atom or molecule. And so all you need for London dispersion forces is anything that has electrons will have London dispersion forces. So this is the only force between nonpolar molecules. So we just need anything with electrons will have van der Waals forces. So even if you're an ionic compound, even if you are a very polar molecule, even if you're nonpolar, all you need is electrons because they can slosh back and forth around the atoms. Get this a little neater. Okay. And so these London dispersion forces, these exist between all molecules. They're the only attractive force between nonpolar molecules, sorry. And these increase with molecular weight, right? So the more atoms that we have in the molecule, the more electrons there are. The more electrons there are, the more you can slosh around. So the bigger the atom, the more London dispersion, or the stronger the London dispersion force is. So for example, if we look at iodine and fluorine, which one is the bigger atom? Iodine. How do you know iodine is the bigger atom? Okay. So yeah, one thing you can say, you look at the mass, that's going to be a bigger atom. And we also know the periodic trend. As we go farther down the periods, right, we add another principal energy level, the atoms get larger, right? So iodine has more electrons. We know the mass, it's more massive. And so it's going to have stronger, two neutral iodine atoms are going to have stronger London dispersion forces than two neutral fluorine atoms.
Does that have anything to do with the atomic radius?
Yeah, that's the size. So that's because it gets bigger, they can slosh around more, right? We have more electrons, and that's also because the atom's getting bigger. As we fill in more principal energy levels, the atoms get larger and larger. All right, am I good to go on to the next? Okay, so the next force are dipole-dipole forces. And so these are forces between atoms with a permanent dipole. Or sorry, molecules with a permanent dipole. Molecules with a permanent dipole. And the reason I say permanent is because London dispersion forces, those were what kind of dipole? Temporary, right? They move around. We'd say they're transient is a fancy way of saying that. The transient dipoles meaning that they just exist for a very short period of time. Molecules that have permanent dipoles interact through dipole-dipole forces as well. And so what do you think tells us, or what else can we determine if we have a permanent dipole? What else have we done to determine? What is another way of saying we have a permanent dipole in the molecule? Yeah, that it's is it a polar or is it a non-polar molecule, right? So these are additional forces. Yeah, additional forces for molecules that are polar. Right? Additional forces for polar molecules, right? Because we still have London dispersion forces. Why? Because they still have electrons. Those can still slosh around. But now, if we have a permanent dipole as well, now we have an additional force there. We have dipole-dipole interactions. And so what this means physically is that if we have something like HCl, hydrogen chloride gas, for example, which one of these is more electronegative, hydrogen or chlorine? Chlorine, right? So that's going to have a partial what charge? partial negative, right? So this is gonna be partial negative, and this is partial positive. And the same thing for this molecule down here. And so this creates a dipole that goes in that direction, and here we have a dipole that goes in that direction, right? We go from partial positive, to partial negative. And this is always there because there's a permanent electronegativity difference between these two atoms. So for these two molecules, they will then arrange themselves in ways such that the partially negative side of one molecule is next to the partially positive side of another molecule. Right? So it's the force between these two molecules. So we arrange ourselves. So partial positive is next to partial negative of different, I'm going to underline that, different molecules. Right, so these are forces between molecules, right, not within the molecule. So in this case, if I highlight things, these are our partially positive charges, and these are our partially negative charges. So here we split up the dipole into its positive side and its negative side. These two molecules have arranged themselves such that the partially negative charge is next to the partially positive, right? And there's different ways they could arrange themselves in the structure themselves. For example, if it's liquid, they can move like this. If it's solid, they'll probably be aligned opposite to each other and have a very ordered fashion. And again, these are additional forces for polar molecules, meaning they still have London dispersion forces, but now that we have a permanent dipole, we've added on this extra type of interaction, right? These are forces between permanent dipoles, which is the same thing as saying forces between polar molecules. All right, am I good to go on? Okay, so the last intermolecular force is hydrogen bonding, right? And so this is a special type of dipole interaction. And it exists between molecules that have hydrogens bonded between fluorine, oxygen, or nitrogen. Exists between molecules that have H bonded to fluorine, oxygen, or nitrogen. So that means for hydrogen bonding to exist, you need hydrogen bonded to one of those elements. And really the ones that are special are oxygen and nitrogen, because those are the elements you're going to see in most biological molecules. They can form the most complex bonds, right? Fluorine really only forms one other bond. The only time it's involved in hydrogen bonding is when it's bonded directly to hydrogen, and then it can't form any more bonds. And the reason for this is just because those elements are so electronegative, and hydrogen only has one electron to share, that it'll really pull that electron, so it's really not shared a whole lot with the hydrogen. All right, so if we have water, for example, or ammonia, NH3, both of these have hydrogens bonded to one of these elements, which means that they can hydrogen bond with each other. And so ammonia, for example, this is what the Lewis structure looks like. we have a special, very partial positive charge on these hydrogens because nitrogen is so electronegative, and then a very partial negative on this nitrogen. And so if there is another ammonia molecule floating around, oops, put it, and it looks something like this. Minus partial positive on each of the hydrogens here. We get a hydrogen bond between this hydrogen here and this nitrogen. We call this a hydrogen bond that exists between them. It's a special type of intermolecular force just because this is so partially negative and this is so partially positive, right? So that's why you get this special interaction here. And so this still means that for these molecules, is ammonia polar or nonpolar? It should be polar, right? Because what would the shape be for ammonia? Trigonal pyramidal, right? Because we have 1, 2, 3 bonding pairs, 1 lone pair. And trigonal pyramidal is always a polar molecule, right? So it still has dipole-dipole interactions. Does it have electrons in the molecule? Yes, so it still has what other force? Van der Waals and London dispersion forces. But now because it has these hydrogens bonded to the nitrogen here, it has another intermolecular force added, which is hydrogen bonding. All right, so it doesn't exclude the other forces from existing. In fact, it includes them. The structure just adds the strength of these different forces. And so, for example, in water, water is unique because it can form 2 different hydrogen bonds, or 4 different hydrogen bonds for every 1 water molecule, right? These lone pairs right here can interact with the hydrogen of another water molecule. This lone pair then interacts with the hydrogen of another water molecule. And what do these hydrogens on this water molecule interact with? It would be the oxygen of other water molecules, right? So there'd be another one here, then they have their 2. Something like that, right? So water can interact with 4 other different water molecules through hydrogen bonding alone. And then it has dipole-dipole forces and London dispersion forces on top of that. So that's why water has unique properties to it, right? So that's why different temperatures of ice and different pressures have different classifications. If you get to high enough or low enough temperatures or high enough pressures, eventually you force the hydrogen bonding structure to change for water. It's also why water, when it freezes, does it become less or more dense? What do you think? What does water do? What does frozen water do in liquid water? It floats, right? If we have icebergs, what do they do in the ocean? They float, right? Titanic learned that the hard way. So they float in the ocean, which means that they're less dense. And that's because as you get to those cold temperatures, the water molecule, instead of having, the water molecules moving around each other and temperature affecting that, all of a sudden they force them into the hydrogen bonding configurations, which means that they spread out, the molecules spread out a little bit to force hydrogen bonding interactions. That means that molecules are farther apart, the compound gets less dense. Okay. And so the strength of the intermolecular forces goes hydrogen bonding, and a lot of times I'll just put H bonding, is greater than dipole-dipole forces. Which is then greater than London dispersion forces or Van der Waals forces. And then if we added an ionic compound here, where would ionic compounds go in our little flow chart here? At the very beginning, right? Ionic compounds would go over here. And so when we're looking at different molecules, we can determine a lot just by the structure of the molecule. Drawing it, determining the shape, we can determine a lot of the physical properties. Because how strongly molecules are attracted to each other tells us about how easy it is to separate those molecules. The easier it is, the less energy we have to put into pulling them apart. So things like boiling point, freezing point, all of those we can get a general idea for a compound or a mixture of molecules just based off of their intermolecular forces. All right, so we'll end a little early today, and next time we'll come back and we'll talk about some specific examples of this, and then we're gonna start moving into chemical quantities, right? So now that we have the idea of molecules built up and how they interact with each other, right? Without going through a chemical reaction, we're gonna start looking at how do things now change when bonds are breaking and forming with other molecules, right? So here, everything is still staying intact. There's no bonds breaking. It's just forces between molecules. Now we're gonna start talking about chemical reactions, bonds breaking and bonds forming. All right, so we'll start lab at 3:25 today. So I'll see you guys up there.